Okay, today we're going to talk about naming and writing covalent compounds of real chemistry. Now, there are two types of main compounds that we're going to look at. The first one's ionic compounds, which, not surprisingly, are made up of ions, but we're going to worry about those later. The ones we're interested in today are molecular compounds. Now, these are made up of nonmetals in groups 14 through 17, and they have a really high electronegativity, if you recall. So they don't want to give up any electrons they've got. And in fact, they really want more. So when they try to fill their valence shells by bonding with each other, they can't just take an electron. They have to settle with sharing an electron. But that's okay. It works. They fill their valence shell like they want to. They can pretend like they're nobility, the noble gases. And when atoms bond by sharing electrons, we call that a covalent bond. Classic example of this is chlorine. Now, chlorine has 7 valence electrons, only needs one more to be full. And you can see where it looks like there's an empty spot right there. That's where these two are by themselves, the one on here and the one here. But if they share, then both atoms could take advantage of that and pretend like they have a full outer shell. See? Now they're both happy. And if you do an electron dot diagram like this, once they form a bond, we turn that into a straight line to show that they've actually bonded. And that takes place between those lone or lonely electrons that were there on the chlorine atom. Now, another example is carbon. Now, I want to show carbon because it forms an astonishing 4 bonds under normal circumstances. And that's the most that an atom will normally form, the most number of bonds. And once it gets its 4, it's got a full valence shell, it's happy. But notice here that each one of these hydrogens on this methane uh, molecule here, each one of the hydrogens only has 1 bond. But it turns out that's fine because remember, hydrogen only has that S 1s sublevel, which is filled when it has 2 electrons. So all it needs is one little more electron, and it's a happy camper. Now, obviously, there are going to be times when an atom is going to need more than one electron. Now, it could either bond with multiple other atoms, or it could form a multiple bond with one other atom. Take a look at this oxygen here. When it forms one bond, it still has lone electrons left, and that's no good. So these lone electrons are actually going to combine and form a second bond. Then it's happy. Each one of these atoms now has a full valence shell, which is what it wants. And whenever you have 2 pairs or 4 electrons involved, we call that a double bond. And as you can imagine, if there are double bonds, they're going to be triple bonds. Nitrogen, an example, when it bonds to itself, it forms a triple bond to get that full valence shell. Now, quadruple bonds do exist, but we're not going to talk about them in our class. So we're going to stick the highest that we're going to go to is going to be the triple bond because that's the highest you get under normal circumstances. And all this bonding does something, right? It forms molecules. And you can have a molecule between one element, like that O2 that I showed you before, or if it's more than one type of element, then it's going to form a compound, like the methane, or as my example here would be CO2. And the properties of the molecular compounds are pretty much what you'd expect, considering they come from nonmetals. They have, relatively speaking, low melting and boiling points. A lot of them are gases, a few liquids. If they are solids, they're going to be a soft solid. They don't conduct heat and electricity very well. They don't dissolve very well in water. And since they don't dissolve well, they're not going to transmit electricity through water. So they're not electrolytes. Now, naming binary molecular compounds. Now, binary means 2. So we're just talking about 2 different elements here. And that's all we're going to do in our class. And naming them is dead simple. First, if you have the formula, you just write down the name of the first element that's in the formula. If you don't have the formula, if you have a structure or a molecule, then you have to figure out which one's the least electronegative. And that's going to be the one that you write down first. Uh, Now, that's the rule. And of course, with every rule, there's always an exception. The exception is if you have oxygen and a halogen together, you always write the halogen first, no matter what. Now, if you don't remember how to tell which one's the least electronegative, It's going to be the one furthest to the left, or it has the lowest group number, and the furthest down if they're in the same group. Uh, and so it has the higher period number. Remember, the closer it is to francium, the least the less the electronegativity is going to be. So that's what you're looking for. That's going to be the first one, the one that's closest to francium. Okay, step 2, you get the second nonmetal, and you're going to change the end of the name to IDE. So bromine will become bromide, fluorine becomes fluoride, etc. And then we're going to put some prefixes on these things to tell people how many atoms of each one of these elements were actually in the compound. Now, a quick little note here. When we write the names of these things, um, if the prefix ends in a vowel like A or O, and the element name begins with a vowel, so you'd have two vowels next to each other, we usually drop the last vowel on the prefix. And you'll see some examples of that. But we never drop the I, like die. We don't drop that. And so you're actually writing two words. You're going to write the prefix, if needed, and the name of the first element in the compound, the least electronegative one, and then the prefix, the stem of the name of the second element, but remember we've changed the end to IDE. Another quick note on the prefixes, we don't put mono on the first element. Honestly, I don't know why. Now, and sometimes they do, but in our case, for consistency, we're we're not going to do that. So we never put mono on the first element. And here are the prefixes that you need to memorize. Obviously, they go above 10, but we're only going to worry about the first 10 here. And a lot of these you already know, mono, uh, deca, this kind of thing. A few of you might not, you may not be familiar with nona for 9. And you have to remember that 2 could be bi in some cases, but in chemistry it's always di. And 4 isn't quad, it's always tetra. So here's some examples. And oopsie, I went a little too fast there. I went ahead and showed you the first one. Dinitrogen monoxide, because you've got two nitrogens. And remember, you don't change the end of the first name. And monoxide, because we have one oxygen, so you put the mono there. And again, we didn't write two O's down, we dropped the O on the mono. And we changed the end of oxygen to ide, so oxygen becomes oxide. So you might want to pause this for a second, see if you can get the rest of them on your own. Okay, now I'm going to assume either you started it up again or you didn't pause. So let's look at this next one. It's going to be nitrogen dioxide. Again, we don't put mono on that first one. Dichlorine heptoxide, dropped the A on hepta because of the O on oxygen. Carbon tetrabromide, good old carbon dioxide, and disulfur trioxide. See, now we sound like real chemists, don't you? Now, writing the formulas from the names when it comes to molecular compounds is dead simple because the name gives you the formula. You just follow the instructions. So take a look at these names. You might want to pause it again for a second, see if you could figure these out. Okay, so you either restarted it or you didn't stop. Diphosphorus means you've got dyes 2, you got 2 phosphorus atoms. Pentoxide means you have 5 oxygen atoms, so that's going to give you P2O5. Tetraiodine nonoxide is I4O9. Sulfur hexafluoride, SF6. Nitrogen trioxide, NO3. Carbon tetrahydride, also called methane, CH4, and phosphorus trifluoride is PF3. And that's all, folks. Thanks and have a great day.